So in this video, we're going to look at the skeletal system, looking at the structure of bone. So that's both at the microscopic level and then thinking about the macroscopic features of bones, and discuss a little bit about bone cells themselves. And we're going to start a little bit out of order with the book. To me, it just makes more sense to go microscopic first, and then we'll look at the macroscopic details. So here we go. We're going to start with the microscopic material, or the components of a bone. Now, osteocytes, as you recall, hopefully, are they're the primary cell that we find in mature bone, and they are found in a little space and a little pocket in the bony matrix called a lacuna. Lacunae, this is plural, so just lacuna. That is the singular. And so here is the lacuna. I'm going to try to outline it for this particular osteocyte. So it's living in this little space in the bony matrix. And it reaches out and it connects to other other osteocytes through these little channels called canaliculi. A canaliculus is a singular, so US is the singular form, canaliculus. Canaliculi would be all of them. And so you can see that they reach out, and here's a canaliculus here that is connecting the lacuna for this cell back to the lacuna for this cell here. And you can even see right there is where the two cells, their cell membranes meet. And so each of the osteocytes reaches out and makes a connection with nearby osteocytes. And it's these cellular extensions that reach through the canaliculi that allow osteocytes to pass nutrients and gases that they require from the blood, from the capillaries, to other osteocytes that are further away from the capillaries. And then those further away osteocytes will pass back the waste gases and the waste products so that they can be dumped back into the blood. So no matter what kind of bone we talk about, we will see that there are osteocytes found in lacunae, and that they are connected either to the outside world, or by the outside world I mean back to the blood vessels, or to each other via canaliculi that allow them to reach out cellular extensions. So bones are composed of different proportions of two basic bone types. There's compact bone. This is the densest bone. And when we looked at the bone in the tissue chapter, as we looked at that kind of bone, we were looking at compact bone. But there's also spongy bone. And spongy bone has a different structure. And so we'll look at those two structures. So we'll start first with compact bone. So we're looking at compact bone here. And in compact bone, the bony matrix is dense, it's smooth, and it's relatively homogeneous. So it's just this similar material, very dense, embedded, with the osteocytes found in their little lacunae. So here you can see osteocytes that are found in their lacunae. So about 80% of the skeleton is composed of compact bone, and it's found so it's the bulk of the bone in the body, and it also covers every single bone. So the outer shell of all bones is built of compact bone. And then there are some other locations in the body where there's a lot of, it's not just the outer shell, but it's all the way through the bone that it is compact bone. So the functional unit of compact bone is a structure known as an osteon. So osteon here is the functional unit of compact bone. And it is these layers of bony matrix all arranged around a central canal. So inside this central canal is where we see blood vessels. So you can see the blood vessels here, capillaries or arterioles and venules, as well as the yellow there is a nerve. So that we have nerve fibers as well. And so here is an osteon, and here's another one. So they're cut in half so that we can see very nicely. And here they've pulled this one up and out. Not that you could actually do that to bone. They are, they're cemented together by bony matrix. And the concentric layers are referred to as lamellae. A lamellum is a single layer. And so these lamellae are these concentric layers of bone matrix that are found surrounding that central canal. And then running from one central canal to the next central canal here are connecting tubes that are referred to as the perforating canals. So they are transverse. They run across the bone while the osteon runs the length of the bone. And so where we see these osteons is primarily in the compact bone of long bones, but it's also found in the outer shell of all the bones of the body. So the osteon is the functional unit, and it's composed of these lamellae. And notice that kind of right there at the interface of the lamellae is where we find the osteocytes, right there at the break between two lamellum. So in long bones, these columns of osteons are found running the length of the bone. And if you the structure of an osteon gives it lots and lots of strength. So trees, to me, they always look like little tree trunks, right? In that long bone, in the middle of the long bone. So they look like these trees that are kind of bound together by bony matrix, and that tree structure is super, super strong, especially when forces are applied at the two ends of the long bone. Imagine, or you can actually do it. Stand up right now and jump up and down. And you are going to be putting a lot of compressive forces on the bones of your legs when you jump up and down like that. It's crazy. It's like some, 6 or 7 times your body weight is the force when you do a jump like that, is the force that you are putting on your bones in order to do this. And so the way that this construction of the osteon, it provides a lot of pushback against that compressive force. So it's very strong in compression. Now, unfortunately, the downside of this construction is that if forces are applied like this from the side, so a transverse force or a lateral force can relatively easily snap a long bone that is built of these osteons because they're just not strong in that direction. It's really about being strong in compression, this microscopic structure of compact bone is. Okay, so compact bone, super strong, especially in compression. So it's got the most strength this way. If you apply lateral forces, that's where it is weak. And so this is how people, like if you were to give a karate kick to somebody right in the middle of the femur, then you could very easy, it is much easier to break the bone that way. All right, come on, you. There we go. Sorry about that. Okay, so the other kind of bone is referred to as spongy bone, also called, dadgummit, sorry about that, also called cancellous bone. Cancellous here. So spongy bone or cancellous bone, I'm going to call it spongy bone. Now, spongy bone is built primarily it's not built of osteons, but instead it's built of these plates. I like to think of them as of that extracellular or of the bony matrix. So rather than being a solid, dense, homogeneous material. Spongy bone has a lot of non-bone spaces in it. So you can see there's lots of this hollow space. Now, it's not empty. What you're seeing is a bone that is dead, and so you can see it's airspace now. But those interconnected spaces in a living bone would be filled with red bone marrow. And red bone marrow, that's the hematopoietic tissue. Dadgummit, I am having a hard time. I keep brushing up against the key that I use to move forward and back. So this is the blood cell producing bone marrow. The red bone marrow is. So with all of this, with all of this non-bony matrix spaces in spongy bone is much lighter in comparison to compact bone, and that makes sense. If you are replacing a dense, heavy bone material with a much more lightweight, water-based material like red bone marrow, then it's going to weigh a lot less. But there's a second advantage that spongy bone allows. So if you recall, with compact bone, that was a terrible bone, but it's really strong in compression, not so strong when lateral forces are applied. Very different with spongy bone. So regardless of the directions that I'm compressing, let's say I were to compress the bone in this direction, I've got a bunch of these trabeculae that are there that are going to help to provide support. Well, what if I compress it in these directions? Again, lots of trabeculae found that are going to push back, that are going to prevent the bone from being crushed. Well, how about if I go at it from this direction here? Can you see any bony plates that are going to be supporting and preventing this bone from crushing in that direction as well? So no matter what direction you squeeze and try to compress this bone, it will be less likely to crush, regardless of the direction. Okay, so spongy bone is not as strong it's not as strong as compact bone is. But you can compress spongy bone from any direction, and it will have the same strength regardless. So unlike our compact bone, there is no direction in which you can compress spongy bone where it's weaker. It is the same strength no matter which direction the force is being applied. So spongy bone is found inside the flat bones, so at the center of the flat bones, in the irregular bones like the vertebra, in short bones, think about the carpals and the tarsals, and at the ends of the long bones. So in this region here and here, we also find spongy bone. So compact bone in long bones is limited to the central shaft of the bone. Okay, so cancellous bone or spongy bone has a really different structure, but that gives it some unique properties. Regardless of which way that you try to squeeze or compress the bone, it has it is equally strong. Okay, so now let's take a moment then and think about the parts of a long bone. And so here we have the femur. It's the head of the femur, the proximal end of the femur. And the ends of a long bone are referred to as the epiphysis. If it's plural, then epiphyses. So there is an proximal epiphysis to the femur and a distal epiphysis of the femur. So why don't you try saying that? If you can say it, then you'll be much more likely to be able to spell it. So look around you, make sure nobody's watching. All right, you can do it now. Epiphysis. Did you say it? Let's do it one more time. Epiphysis. Okay, let's say it together. 1, 2, 3. Epiphysis. All right, so if you can say it, you can spell it. So the ends of the bone of a long bone are referred to as the epiphyses. And they are filled, as you can see here, with not compact bone, but spongy bone in the center. So this is spongy bone here, and this is spongy bone as well. And I should say, spongy bone is not like soft and spongy. It's only the appearance of sponginess that we see with spongy bone. Now, it's also covered by a thin layer of compact bone. So all of this is compact bone. And then anywhere that it is inside of a joint capsule, then there is also a layer of what is called well, you know what it is. It's covered by cartilage. And the cartilage type is hyaline cartilage. Remember, this is the one that is very smooth looking. And the hyaline cartilage there helps to absorb the stress that is placed on the joint, and also to kind of smooth out the movements of the joint. So they help to reduce the friction of the joint. Okay, so the epiphyses, those are the ends of the bone, and there's a proximal and distal epiphysis. It's filled with spongy bone, covered in compact bone, and then anywhere it's inside the joint capsule, it has this hyaline cartilage there to kind of smooth the movement of the joint. So in between the two epiphyses is the diaphysis. That's the shaft of the bone. And it is composed of this very dense, very strong, compact bone. And so here we're looking this time at the humerus, and we can see they've sliced this humerus down the middle, and you can see that there is an opening inside. So it kind of starts here, and it runs down to here, surrounded with some spongy bone. So this is spongy bone kind of in that area as well. And that space in there is referred to as the medullary cavity, sometimes referred to as the marrow cavity. We'll call it the medullary cavity in this class, though. And so that's a central hollow chamber, and it's filled not with red marrow, the blood cell producing marrow. Instead, it is filled with yellow marrow. And yellow marrow is yellow because it has a lot of fat in it. There's a lot of adipose tissue in yellow marrow. And so this is storage, energy storage, that we use this, take advantage of this space in the bone. Okay, so here this time we're looking at, what is that? That's a fibula, it looks like. So, they shouldn't use words like superior and inferior. Instead, it should say proximal and distal epiphysis. And then the diaphysis in the center. Okay, so what else, what other features do we find on bones? And so all bones have an external covering called the periosteum and an internal lining known as the endosteum. So the periosteum, and you can see the periosteum here, it's kind of come away from the bone. Probably in the process of sawing, it was loosened up a bit. That is unusual. In life, this would not happen because there are fibers that extend deep into the bone from the periosteum. So the periosteum is a tough, fibrous connective tissue. It's a dense, irregular connective tissue, meaning the fibers are kind of going every which way. And it covers the external surface of the bone. Fibers are continuous with the fibers that are inside the bone. And then out at the bone ends, so here, I know we haven't talked about muscles yet, but there are muscles there's connective tissue in the muscles that kind of, if this is where the muscle is, so here's skeletal muscle, extending out from the end of the muscle is connective tissue. It's dense, regular connective tissue that makes up the tendons associated with the muscle. And then there can also be ligaments that are connecting bone to bone. And so the fibers that are found in the periosteum are continuous with the fibers that are found in the ligaments and the tendons. So, I'm having all kinds of problems today with the slides. Sorry about that. I'll try to do better. So that creates a really strong connection between the muscle and the bone, or between the ligament and the bone, because these fibers are interwoven and interconnected and continuous from one structure to the next. And it makes it difficult to say exactly where the tendon ends and the periosteum begins. So this also provides a route for blood vessel and nervous supply. So there will be blood vessels found in this periosteum layer that provide, that supply the bone blood vessels and also the nerves. So that's the periosteum. Peri means around, so that's the covering that is around the bone. There is also the endosteum, and that lines the medullary cavity here. And you can see the yellow marrow inside the medullary cavity. It's kind of gray color. This is a preserved bone, so it doesn't have the same coloration that you would see if it were living. And so it's a thin connective tissue lining that is found lining the medullary cavity, and it also covers the trabeculae of spongy bone. And so this is the trabeculum here, a trabecula. Here's another trabecula here, and there is a layer of endosteum that covers over the trabecula. And this is where we find the bone-forming cells that are going to be involved in bone growth and bone repair, and a process that's known as remodeling. Just like you could remodel a house, our bones are constantly being remodeled as damage occurs. Okay, so those are structures that are found regardless of whether it's a long bone or short bone. All bones have periosteum and endosteum. Okay, so let's take a look now at the types of cells that we find in bones. So osteogenic cells, these are the progenitor cells. They're found in the periosteum and the endosteum, and they're also found in the bony canals of the bone that contain blood vessels. So anywhere that we could find blood vessels, we're going to find osteogenic cells. Osteo meaning bone. Gen, think Genesis. These are the bone beginning cells. So Genesis is the beginning of the Bible. Genesis means the beginning of something. Osteogenic cells are the stem cells that can divide and produce osteoblasts. So they're the only bone cell that is capable of reproducing. And when they divide, one of the daughter cells remains an osteogenic cell, and the other is fully differentiated and is referred to as an osteoblast. Osteoblasts are the bone-forming cells. So when we need to make new bone tissue, then an osteoblast is the cell that is required to do it. So here you can see an osteoblast out at a surface of a trabeculum or some other structure. But here, there's a bone cell found inside its lacuna. Once it becomes trapped in its own little bony chamber, then we would say that it has matured into an osteocyte. So the osteoblasts, if they were to become more active, what do you think would happen to blood calcium? Now I've written there that it decreases blood calcium, or the amount of calcium that's found in the blood. But why would that be? Well, it's because these cells are responsible for making new bone. So they're going to be drawing calcium and phosphorus out of the blood and using it to build new bone material. Hopefully that makes some good sense. The reason I'm making a point of that is because in a little while we're going to look at how, in a later lecture, we're going to look at how we regulate the amount of calcium that's in the blood. Okay, so osteogenic cells can divide, and one of the offspring cells is an osteoblast. So once an osteoblast is fully enclosed in its lacuna, then we would say that it is matured into an osteocyte, and these are by far the most numerous cell in bones. The osteocytes are, because they're already trapped in there, and their job is to tend and maintain the bony matrix that's right around themselves. So they can secrete new, or they can secrete reinforcing bone matrix, so they can take calcium out of the blood and phosphorus out of the blood and create hydroxyapatite and calcium carbonate to reinforce the bone around them. And they can also produce the protein fibers that are there, making that bone not just hard, but also very strong. So osteocytes are just mature osteoblasts. They do a lot of the same stuff. Don't know why that came up either. Dadgummit. I'm sorry, guys. Yeah, hopefully y'all are laughing with me each time one of these foolish things happens. Okay, so the last kind of cell that we see in bone is referred to as an osteoclast. Osteoclasts are the bone-destroying cells. You might ask yourself, why is it that we would want to destroy bone? Well, imagine if you damage the bone, put in some little tiny fractures in the bone. Well, in order to make the bone strong again, we have to go in and clean up the damaged bone matrix. And it's the job of the osteoclasts to do that very thing. They can produce acids that will dissolve the calcium phosphate salts, and they can produce enzymes that will break down the protein fibers. And so between these two materials, they go in and dissolve bone material. And so by their activity, what will happen to blood calcium levels? Well, if you're not just reading ahead, you can probably reason your way to the idea that if they are dissolving bone matrix, hydroxyapatite and calcium carbonate, that their work will increase the amount of free calcium ions that are available in the body fluids and in the blood. They are an unusual cell because they are multinucleate. So we've talked about skeletal muscle cells as having many nuclei, or being multinucleate. Well, these guys are also multinucleate, and they form as several white blood cells fuse together to make this one very large cell. So osteoclasts, the bone destroyers; osteoblasts, the bone builders; osteocytes are the bone maintainers. All right, so the last thing that we are going to talk about in this lecture is some of the markings that are associated with the bones. And you say, markings, huh? Did somebody mark on my bones? Well, it's not necessarily that somebody marked on the bones, but because of the function of the bone itself. It has different lumps and bumps and bulges that all are associated with the work that the bone is doing, with the function of that region of the bone. And so on page 215 in the chapter, there is a long list of different kinds of bone markings. The depressions, the bumps, the bulges, the holes, other features that we see on the surface of bones. And these are sites for muscle attachment, points that articulate, or they might be holes and passageways for blood vessels and for nerves. So I want you to pay close attention to Table 7.4, because these terms are explaining the bone markings that you see in the drawings that you are learning. So, for instance, if you put your hands on your hips, standing with your arms akimbo, you're putting your hands on what is known as the iliac crest. It's a crest on the ilium of the hip bone. A crest is a narrow ridge-like projection, and so it's like a topmost area, or it's a ridge that sticks up. So that's a crest. Here we see a rounded end, a knob-like process, a tuberosity maybe. This is better described as a tuberosity. Yeah, I shouldn't have brought that one up. I'm not sure exactly what you would call that. I'd call it the head. But it's and as we talk about joints, we're going to describe it as a ball and socket joint. But you can see that there are all of these tubercles here along the length of the long bone that are sites where muscle attaches. And because we're tugging at the bone there, then it gets reinforced. These processes build over time as we use and stress the bone. So a fossa would be a big dish-like pit or a deep pit that's relatively large in a bone. A fovea would be a small little pit or depression. A meatus is a tube-like passage. A foramen is just a hole through something. So all of these different terms. Oh, and by the way, foramen, that's one I want you to pay specific attention to, because that's a hole that blood vessels and nerves especially go through, so that we can feed muscle and other tissues that are on the opposite side of a bone. And so within the head, within the skull, there are a number of foramina. So lots of different bone markings listed there on page 215. Be sure that you pay good attention to this and make sure that as you're looking at the bones, you'll be able to recognize these structures. Okay, so there we have it. We've talked about the microscopic structure of both spongy bone and compact bone. We've talked about the macroscopic structure of a long bone, some of the tissues that are common to all bones, especially the periosteum and the endosteum, and then a little bit more on some of the anatomical parts. So if you have questions, you know how to reach me.